Okay, let's get started. So the topic I'm talking about today is quite long-winded. So I'm not going to repeat that topic, but the next slide, I'm going to show you what I really want to talk about today is really the importance of building a better conceptual model is really the first step, and it's the most critical step in building a better water balance, water quality model for waste rock dumps and for tailings storage facilities. And oftentimes we don't spend nearly as much time on the conceptual model phase compared to what we spend on the numerical model, and that's something we need to improve as an industry. So what exactly means for building a better conceptual model? Well, it means we really need to have a design basis first, then everything else. Half of the time, that's not done. We don't even have a design basis. Half of the time, we're often handed a design basis that are 5 years old by our clients, and 5 years is a long time in the mining industry. Design basis is supposedly to be a live document that needs to be constantly updated as new information emerges. And at this point, I want to selflessly, I want to promote the design basis memorandum guidance document developed by the Landform Design Institute. I think that's something we really need to look into, and that's the basis we should build our design basis memorandum for each mine site. The second bullet point is more technical. It has to do with the order of things. We often talk about water quality models on its own, but to build a water quality model, we really need a good handle on the water balance first. And that's sometimes not half of the time, that's not even done. We often run into cases where we have a water quality model without any mentioning of water balance. So we like to promote that water balance, water quality model should really be together. And lastly, water management first, before that water balance model kicks in. And that does not have to be sequential. Sometimes once we have the water balance model, we want to look back into our water management plan, and then that iterative process should be really the norm in the modeling development. So what? Why are we talking about this? Because while almost every report you are reading or every study you have those diagrams, there was what we perceive as a conceptual model. So why do we need a better conceptual model? Well, there's that transition when we build our conceptual or mental model. We often jump straight into our numerical models, and that contains high level of complexity and a high number of elements looking at a very specific area of the mine site. I think what's missing is the in-between steps. I think we really need an intermediate model between that conceptualization and the numerical model. But to different people, the concept complexity is different. For someone who manages hundreds or thousands of gigabytes of model, your traditional numerical model may be too simple. For someone who manages 1D model, their ideas of complexity can be very different. So that's why I like to present two case studies. Case study number one is more on the side of a little bit beyond conceptual model, but before we hit that numerical modeling world. And the case study number two is moving slightly beyond toward that numerical model. These are two real projects we worked on and two different concepts we experimented. So before I jump into the case study, so why want to do the intermediate model? It's really ideal for landform scale. So we're talking about a waste rock facility, a tailings storage facility at the facility level. And those intermediate models, because they have the right complexity, they can be integrated into your site-wide water quality, water balance, water quality model without significant effort. And then lastly, it does provide that opportunity perhaps before we go into the numerical model to right-size our conceptual model. There are things that we might discover that are counterintuitive, or we might discovered that our biases, those biases, mental biases in our conceptual model that we often can miss in the numerical model, right? So the first case study I want to talk about is it's what we call a fully instrumented watershed. This is one of the first projects that the company O'Kane has worked on. There are countless consultants, countless research institutes that have worked on this project. The site is in Syncrude at northern Alberta. The site is part of the larger landform, closure landform design that consists of an upland followed by a series of wetland and peat lake system. So what this landform is focused on the upland component of that closure landform. So we have the upland is created by a saline, highly saline solid overburden material as a result of oil sands mining. We're talking about the clear water clay shales and the glacial tails material that you have to excavate to access the McMurray Formation in the oil sands. So it's a well-instrumented site. We monitor everything to the bones. Everything that hydrologists or geochemists can dream of. We measure the water storage, the volumetric water content in the reclamation material, in the cover system we designed, in addition to the climate, and the runoff interflow. So everything you can dream of in this watershed. It's very rare. We often don't do that in the active mines. So as I mentioned, there are countless models. There are countless numerical models as a result because of that monitoring data we have. But what we did here differently a couple of years ago is to take a step back and look at what we are missing in our modeling, or what we're missing in our conceptualization. So that leads us to what we call a causal loop diagram, or CLDs. There are particular ways to construct those diagrams, but I would like to highlight a few important points. Those diagrams are constructed collectively, so they're never done by one single consultant or one single discipline. What you do is you gather all the disciplines together. You have a mapping process, a workshop process to map out all the variables that matters to each discipline. You map out what we call the stock variable. So that's the water storage. In this particular example, there are many more of them that we created for this site. So, and then there's plus and minus signs. That's the correlation between each variable. So the plus is a positive correlation, minus is a negative correlation. And then from those correlations, you can identify the feedback processes that's driving the water storage stock variable. So as you can see here, there are three major feedback processes. We identified the volume change, it's a positive feedback, and the unsaturated flows. And the other feedback we identify is the evapotranspiration processes. And that's a surprise. So the direct outcome of this creating those diagram exercise is that we identified that the ET processes have been ignored or simplified in the past, where it's simply serving as a model input. But in reality, the evapotranspiration is a feedback loop between the atmosphere and the cover system itself. So it's a highly interactive coupled processes. So that leads to the direct outcome of that is leading to more investment and resources developed to look at the evaporation, the actual evaporation of the cover material. And on the right, and the last point I want to highlight is those feedback processes. You can derive the system behavior from those feedback processes. If you are in modeling for simulation for a long time, you know that system behavior, you can throw any system behavior into any of the 6 categories, right? If you look into your water balance or water quality models. So those feedback processes will tell you how the model is going to behave. For example, the positive feedback is going to lead to exponential growth, and the negative feedback is going to lead to goal-seeking behaviors. And when you combine those feedback processes together, that's what's generating the oscillation, the overshoot. And that's become more complex, and that's when you need modeling. The second case study is, so let's switch gear a little bit, moving away from northern Alberta to Australia. It's a legacy mine in southern Australia where it's constantly raining, high rainfall scenario. We have an open pit that's sitting on top of a mountain. And right now there's a pit lake, but the eventual closure plan is to backfill that pit lake with waste rock, acid-generating waste rocks and create a water-shedding landform. So very different from the pit lake system we see in the oil sands. So for that project, is slightly more processes involved than the diagrams. We built a Gaussian model that incorporated all the important physical processes in the model. And the results that we created a tornado chart to look at what's the ranking of variable, which variable is most important in terms of the key performance indicator we're looking at. For example, the seepage. If we want to look at the seepage, and in this particular case, it's the parameter n, how fast the waste rock will desaturate. For seepage, n is not that important, but for degree of saturation, n is very important. So that helps inform the construction, the backfill processes, where perhaps toward the bottom of the open pit, we can have less compaction because that's where seepage is not critical, where the oxygen will penetrate less. Toward the top of the open pit, that's where we need to beef up our compaction effort and the deposition planning a little bit more. So this case study showed that water balance model is not just a precursor to water quality, but rather you can inform construction, your mine planning, using your operational water balance models. So key takeaways, again, I like to emphasize conceptual model first, then everything else. And water balance, water quality can indeed inform construction, as shown in the case study number 2. But we also need to make sure that water balance is done first, then water quality. Water quality is a lagging indicator. When you see something bad in the water quality, you are too late. So you really need to want to focus on one of the leading indicators, so that is water balance, among others, before you look into water quality. And lastly, is that transition between the water balance, between the conceptual and the numerical. That's how we can build a defensible model down the road. So thank you.
Hello, thank you very much, Tony. Do we have questions for Tony on his presentation today? We have one. We have a microphone.
Thank you. So, hi, Tony. Nice to meet you. So, I have a small question for you. So, for the causal loop diagram you show us, I'm just curious what kind of software or program you're using to conduct that model, like Goldseam, I guess?
Sorry, which one?
The causal loop diagram you show us.
Oh, this
like
one
in
here.
What?
So that's created in Vansim. It's just another, it's very similar to Goldseam, but not exactly the same. It's created in that software. But really, you can do this on the whiteboard.
I see. Okay, thank you very much.
Yeah.
Great presentation. Can you talk a little bit to the choices we make regarding process parameterization in these intermediate models and how they may lead to model structural deficiencies that can cause us to make choices down the road when we go to a full-fledged numerical model that may be misled? So what I mean by that is, you point to this parameter n. What does that mean? How does that overlap with the real physical thing? And what's our confidence about that relationship? How do you develop that with confidence?
I think so. During the mapping processes, if you're talking about a very narrow problem, like in the case study 2, we're looking at specifically at the backfilling processes for the open pit. So it's a very specific problem. So we're really looking at how to minimize 2 problems: oxygen penetration once we have the backfill, because it's highly sulfidic, the waste rock, and then the transport problem. So it's a seepage, if there's any, from the backfill downstream. Remember, the open pit is sitting near the top of a mountain under a high rainfall climate. So that's how we kind of narrow down our focus. Then from that narrowed down processes, that's where the unsaturated properties come into play. The N, for example, in the Van de Newton parameters, that basically tells you how fast it's going to desaturate. And how fast desaturate is going to provide you a timeline or magnitude in terms of how much water is going to stay in that backfill and how much air is going to get in. So I think that mapping process is really what that's important, and that's more challenging when you have a bigger project with multiple disciplines, because everyone has their parameters of concern, so to speak. Yeah.
Yeah, thank you very much. We have time for one more question. And if there is none, yeah, help me just thank Tony here.
Thank you.